Welcome to the In-Memory Computing Summit. My name's Neil Stevenson from Hazelcast. I'm going to be talking today and doing a demo on machine learning. Not really about machine learning, but deploying machine learning, using machine learning, actually doing something valuable with it. We're due to finish 25 to 3. I'll stop about 2:30 and we can have some questions. But we'll start with a question. Quite an obvious question, 2 answers. As a bit of added value, there's the answer. What came first, in my opinion, is chicken. So, what's that a picture of? It's a chicken. Chickens, to me, are a little bit like in-memory computing. Does a couple of things. Doesn't solve all the problems in the world. More specifically, this chicken is my chicken. I live out in the country. And for the very astute, this is a special breed chicken. It's a Bresse Gauloise, so it's not quite the exact same as any other chicken. It's not your typical image of a chicken, but you recognize it as a chicken. So we'll come back to why I put a slide up about chickens. So this is quick introduction to stream processing. Some of you will have this, some of you won't. Stream processing for business is about making money, solving problems. It's just another way of doing things. It's a way of doing things faster, more predictably, scalable, all the kind of nice stuff, securability, reliability, all the illities, as they say. Latency and speed are the keys. It's like how much data can you push through? How quick can you get your answers out? Latency and speed is always like that thing of the waterfall. How much water goes over? How long does it take from top to bottom? Some things you can change, some you can't. I work for Hazelcast. We have a streaming engine. Other streaming engines are available. Fundamentally, they do a similar kind of thing. There's a question of preference. But really what we're talking about is you've got big data coming in from somewhere, too big to store, too big to process. When I started in computing, you would store some data, do an overnight batch, got your result out. I mean, dinosaurs roamed the earth. It was like just a wrong way to do it. You couldn't do things quickly. Now, with Internet of Things, you're getting so much data coming in, you can't afford to store it and then process it later. You have to process it as it happens. So what we have on this diagram is on the left, we have multiple data sources coming into your business from somewhere. Is it clicks? Is it sensors? Is it real-world events? And you kind of want to do something with that data. You want to process it and perhaps store the output, and perhaps even store the input, but you'll never look at that input again because there's too much of it. So, very quick heads up on stream processing. Stream processing is just a paradigm where you move data from place to place and process it. Processing it meaning reduce it down, some sort of aggregation. Process it meaning expand it out, some sort of redistribution. Processing meaning deplete it, like a projection in SQL terms. Processing like filtering it, like a selection in SQL terms. Or enrich it, add some extra data in based on data you already have. The demo today will be Hazelcast Jet, Hazelcast streaming engine. As far as we're concerned, it's just a Java dependency. You embed it in a jar file. Picture on the left, 3 jar files that connect together. Dead easy to get up and running. Picture on the right, you might have those jar files taking feeds in from other places, from other languages other than Java, so not necessarily jar files. And when I mentioned enrichment from where? If you've got a piece of data coming in, say it's a price of something, you want to enrich it with some information, perhaps multiply it by a certain factor. Well, you've got to get that other data from somewhere, and it has to be fast. So in-memory computing is the answer. So take a very, very quick look at use cases. Stream processing is for most people, about infinite streams. You've got data just coming in forever and ever and ever. You can't do a batch, you can't stop, you can't wait. You want those answers right now. What we mean by real time is nearly right now. Data's coming in, you've got to process it. There's always a time lag. It might be nearly instant. That's what we mean by real time. As fast as it can be, because time, as we'll come to see, is money. And you can do other things too. You can make that part of a transformation, like an ETL. I believe the slides are distributed afterwards, and for people who are watching on catch-up, you get to hear my voice, but you won't get to see the demo particularly well. And you can do other things with stream processing. We can do what we call edge and fog compute. So edge computing is where you have a smallish processor, perhaps a Raspberry Pi, out in the outside world, taking in some data, depleting it down, doing some sort of aggregation, that first level of processing. Fog is kind of the same idea, but more on a touch point into the cloud. So you might have an edge computer is out deployed on a supermarket trolley, and that might be feeding data into head office, and they're doing a first pass on a cloud node before passing that on to the next stage. So it's all about reduction and processing as you go. So really, stream processing, what interests us? Performance, obviously, but also ease. It has to be easy to get going, easy to work with if you're a developer, easy to run if you're an ops person, easy for your environment. You might be on bare metal, you might be on AWS, you might be on Azure, whatever you want to deploy it, it has to go. So, stream processing. There's some that think stream processing has passed through several waves, several evolutions. The first I came across stream processing was Hadoop, MapReduce. Hadoop is fine, does the job. Your data is sitting on disks, you can do a processing off that, you can get insights out of that. Fundamentally, that's okay. You have to store the data first, so you've got to pay the price in terms of storage and pay the price in terms of actual rotational delays on your disks, because they're still rotational disks. So it's not great for everything. It's fine. The kind of second iteration was when in-memory came along, the likes of Spark. Great boost in terms of performance, a little bit of fuss to get going. Maybe not the biggest problem in the world, but the biggest problem in Spark terms is kind of that batching. It's like we take a chunk of data and then we take the next chunk of data. And realistically, your data just arrives all the time. So how do you work out when the right points to take chunks are? Which leads us into type 3, which is the more modern ones where your data is being processed continually. It's not working off batches, you're working off windows onto the same data. So something that happens at 1 minute to 10 and something that happens at 1 minute after 10 is not necessarily in two different batches, just in a window on that continuous stream. And it's all about ease. A quick hands up, anybody a Unix developer? One person is going to admit to it. I was. This is where I first came across streams. This is Unix. What that is, if I go on, it's a directed acyclic graph. It's a stream of processing where we've got some primitive operations that we chain together to do something. The list operation, the ls, lists some files. The tr operation turns uppercase letters into lowercase letters. It's a transformation. The grep is a filter, and the last bit at the end does the result. That's a stream. As far as the grep is concerned, it's an infinite stream. This data is just coming in, it goes out. Grep doesn't wait for anything to happen before it puts output. Every piece of input contributes to output. I want to get on to the machine learning. We've done some benchmarks of Hazelcast Jet. It's very fast. Now, obviously, you can benchmark these things yourself, and it's a good thing to do. But now on to AI. Machine learning. It's the future. You know, there's various trends we all kind of hear about. You know, microservices was popular. Now people are starting to think about these pervasive computing engines. I've got bottom left corner, Amazon Alexa. It's listening to all the things you're saying. Second from top left. We've got sensors in our homes. We've got drones out there telling us things. We've got machines with cameras on them. All sorts of things. If you look up my LinkedIn picture, you'll see me, and it's like, whoa, you know, these cameras are everywhere. And there's a number of aspects to that around privacy, but fundamentally what's driving it is profit. What can we profitably do with cameras? So that's what AI is about. It's about, in this case, that recognition of images, which is why I put up a picture of a not entirely typical chicken. So what we're going to focus on here is the machine learning part. I am not a data scientist. If you ever see some of my code, you'll wonder what I do. But machine learning is about an algorithm that you deploy that takes some input and gives you an output. And the learning part is that you train these algorithms. You feed them lots and lots of input. People that were here for the talk before lunch will have heard somebody mention, 2 million inputs, took half an hour to train an algorithm. So that's the kind of thing people will do with machine learning. If you're a data scientist, you craft your machine learning algorithm, you blast some data in it, you get out a trained model that is trained to react to certain things. What does a chicken look like? Well, let's give it lots of pictures. This is a chicken, this isn't a chicken. We'll pass enough through and it will figure out what a chicken looks like. So in terms of data science, what we're talking about here is we will have a data feed. That's our data ingest. We want to enhance that data somehow. In this case, we're talking about with context. We want to take that context and add some meaning to it and make some sort of prediction. If we take cameras, imagine I've just arrived at Heathrow Airport today. A camera's looking at my face. It recognizes me. It can maybe add a bit of context knowing what flight I've come in on. So it could perhaps say I'm in a bad mood and my flight's been delayed 2 hours. Perhaps that's connected. Then he's going to predict, well, Neil's going to punch somebody because he's super annoyed. His flight's late, he's missed his connection. That's the kind of information. I'm not going to punch people, and I would heartily recommend you don't do that. But that's the kind of thing you might be looking out for. Who is going to kick off? Who is got like a bad mood on their face? Why might they have a bad mood on their face? Are they just an unhappy person? Did they get drunk on the plane? Is their flight late? That's the kind of contextual information. So the ingest stream will be the stream of pictures. The context is something a little bit more fundamental, like this is their flight. And what you derive from that is how likely are, they're a known troublemaker. What are they going to do about it? And the reason we want in-memory here is just about speed. Speed, speed, speed. The faster you can get this information out, the more value it is to you. It's what we might call perishable data. The faster it gets, if I've come in at Heathrow Airport and you derive the fact that I'm in a bad mood half an hour later, well, I've gone. I'm through the airport, I'm out. You can't do anything about it. Or I'm in a good mood. You can't decide to try and sell me tickets for the Heathrow Express. These are the things you might need from a business perspective. And then there's the operational side that you have to have this elasticity, resilience. Your data model's going to run all the time. It has to be able to increase at peak times, decrease at quiet times, save a bit of money, and keep running. So just the last bit on this, the basic idea is we're going to have a data model which is taking a live feed. That data model's been trained to recognize attributes in that data. We might enrich that data model with some sort of lookup. If we're looking up a relational database that sits on a disk, it'll be too slow. We need to look up something in memory, something that's going to happen fast. Speed matters. I heard this mentioned a couple of times already today about credit cards, and you've got like a couple hundred milliseconds to do things. When somebody basically blips their card, you do a tap and pay, you've got a certain amount of time for the machine to blip, and that's you. That's fine. We want transactions to pass through quickly, but we also want to detect fraud. Heartily recommend, another little bit of side things, get yourself a card reader that blocks your wallet. Because it's not just about individual transactions. Imagine the scenario, somebody, a bad person on the London Underground just goes around, blips everybody's contactless card. Train comes out a tunnel, I don't know how this really works, but that will release a set of payments. So what you're not looking for is one bad transaction, a stream of bad transactions all coming from the one terminal. So that's something where you couldn't keep looking up a database, as this terminal made a lot of changes. This terminal made a lot of changes. The response time would be too slow. So for credit cards, it's all about time. I can remember getting calls from my bank saying, we've blocked your card for safety purposes. Yeah, but it's like, you called me hours after the event. That's no good. Stop it. If you can detect my transactions faulty, don't apply it. And obviously, there's other things you can be doing in terms of transactions. You can be looking for chances to make more money out of the customer. You're buying something. Why don't you buy something else as well? Premium delivery, perhaps, an extra 5%. Which kind of leads us into e-commerce. So for e-commerce, what you might be looking for is somebody pausing. If you ever do any online shopping, it's like add to basket, add to basket, add to basket, proceed to checkout, enter address, payment details, click buy. Well, what happens is people will pause on certain pages. Why did he pause on the buy page? If you can connect that to some external event, like the Game of Thrones finale is on, maybe that's why they've paused. Does this person habitually pause when they're paying just to double check the 3 digits on the back of their card? Is this something where we're in danger that they're giving up? If you're a retailer, you want to maybe do a right then and right there offer. Some pop up on the screen. Click within 5 more minutes and you'll get another 5% off. Okay, I really don't know what will happen now because this is a live demo. And it kind of depends on a number of factors, how well my webcam works, the lighting in the room. The data model we're going to use today is a thing called CFAR. I don't know if that's how it's pronounced. I've never heard it actually spoken. It's a Canadian data model. What they've done is they've given it 60,000 images, saying this is what a cat looks like, this is what a dog looks like, this is what a frog looks like, this is what a horse looks like. And saying, once it's been applied to those 60,000 images, it has a rough idea of what these things look like. So what we're trying to do is determine what an image looks like. Now, this is not as sophisticated as I said earlier at the start about recognizing if somebody's happy or sad. It's only a demo. It's the same idea, though. What we're trying to find out is what kind of animal is this? So, before I go on, let me just, I have in my hand a pack of images. There's the chicken again, there's a horse, a sheep, a pig, a dog with a pig in front of it, a horse again, a cat, the same cats before, and a plane. And me on a bike. These were all images that it should be able to recognize because it's been trained to recognize what a cat looks like and so on. But really, let's find out. So I have the images here on a piece of paper. I'll try one or two. Maybe it'll work, maybe it won't work. We don't really care. I will give you a link at the end to where you can actually download this code so you can do it yourself if you want to try. But where we're going to go, first of all, let's build my code sample. Yeah. That's about right, yeah. Give it a second to do the compile. And what we end up out of this process is a jar file, a standalone Java application that I can deploy somewhere. Come on, there we go, it's done. So one of the places we might choose to deploy it is to Docker. There we go, it's off and running. So there's my stream processing engine up and running in a Docker container. The point for a developer's perspective is this is dead easy. It's just a Maven build that builds us a Docker image, then push it to Docker. And then if you've got Kubernetes or whatever, it can then take over and it can do that scale up, scale down. I'm not running Kubernetes on my laptop because it's just too much fuss today. But let me just try running that here. So basically it's just a jar file, standalone jar file. I've added a couple of little bits to it, but basically it's an Hazelcast memory grid with a Jet stream processing engine. That runs in a single jar file. There we go. Can we see that clearly? Make it a bit bigger. This is the part we want. Our grid has got one JVM in it. We can see that from JPS. And if I start another one on the same laptop, it's not a great idea because they're just competing for resources. Realistically, you'd run it on multiple machines, but they join together. And now we've got two stream processing engines. So we can now cope with twice as many images coming in just by scaling up, scaling out. And because we've got two, we can cope if one fails. If we had 9 and one failed, you've got 8. So you can do that scale up, scale down, and it's all handled for you. So that makes life a little bit easier. So the kind of takeaway point from there is if you're an ops person, it's just a jar file, dead easy to deploy. It's a Docker image, super easy. Kubernetes can control it, all easy peasy stuff. Resilience and scaling comes out the box, so you don't have to worry. And right, so how many copies am I running? I'm just running one. So the one that was there has noticed that the other one has gone away. So now let's try the actual just to see what's going on. I'm going to there we go, open up a web console. In-memory data grids and things like that aren't particularly visual. So you need some sort of monitoring tool to see what's happening. There we go. So I have got no jobs deployed. My data grid is ready, it's running, but I don't have any machine learning. And this is the second aspect that the data scientists will give the ops team a model. Here's the new version of this model, or here's the first version of this model. We need to deploy that to the data grid, which is what I'll do now. But I can't remember the exact command, so I've written it down. There we go. And basically what we're doing now is we're just saying the data scientist team have given us a jar file, their code. All we do is push that across the network. Fantastic, it's actually working. The webcam is working, so those of you can see, this is my webcam input. I'll move that to one side. And there's the webcam output. And what it's doing is it's processing the images. So the webcam input is being fed through the data model that I've just deployed to the grid. And what the data model is trying to do is work out what it's actually getting in the input. So in the input right now, there's a hand, and it hasn't a clue what that is. So this is where I'm going to try some images. Let's try me on a bike. I need to get this in front of the webcam. Let me just move these bits. It depends on the lighting. And see if it... Okay, so what we're looking for... No, it's not got that. Let's try... I did say there's a little bit of ambiguity as to whether it will actually work. Let's try number 2. Let's try plane. All right. If you can see in the top corner, there's a score for what it thinks it is. And it seems to think it's a cat. So this data model's not... Is it a bird? Is it a plane? Maybe it's looking at the other side of the paper. Let's try it again. If it says cat again, then this time it's got it right. What does it say? Deer, cat? Yeah. It's only a demo, you know. So this is the bit of the demo. We'll do one last one just to see. What shall we try? We've got to do the chicken again. There's also a bit of a score comes in on these things. What does that say? I can't see it because it's in front of my screen. Cat. Okay, so Tim Berners-Lee was right. There's a lot of cats on the internet. Really, the point of that is that's still not bad. It's like it's actually recognized something. It didn't get it right. Got it nowhere near right. You know, what was it, a cat, and it was like an airplane or something? But it's starting to get there. I'm just holding a picture in front of a webcam. It's not like brilliant, and there's lights and all sorts of factors, but you've got to figure that out. So what we'd want to do now is take that input and do it offline and reapply that and redeploy that model. We would retrain the model. The model got the wrong answer, but it's only working off the input it's got. So it's been given 60,000 images to give it an idea of what a cat looks like as opposed to a bicycle or a jet airplane. And it's doing the best it can, and it's not doing it very well. So that's where you retrain. That's where you do that offline and redeploy to your data grid again. So I'm just going to wind this down. But just on one last piece, if I wanted to do an operational side, where am I? What am I looking at? There we go. So my model is running. That's it. And what I can see from my model is how much input has passed through it. 406 images come out the webcam because it's clicking them every so often. And realistically, you know, you're going to have thousands of cameras. What are you looking for? You're looking for just little nuggets. There's lots of people passing through an airport. Which one looks unhappy? Well, it's just based on what you observed from one particular picture. You're not going to get it right. It's a aggregation kind of thing. You do lots of training of your model. It gets better it can keep getting better because it will get things wrong. Everything that's wrong is like a learning point for the next one. So let me just close that down. Right, so back to my presentation. Tim Berners-Lee was right, too many cats. Well, so the important thing is your processing is going to be wrong. Wrong first time, wrong every time, because you're training it. It's getting better and better. You want to be able to deploy a new model to a running data grid. You don't want downtime. If you're doing some sort of analysis of credit cards, say, then there might be points where it's convenient for you because it's quiet. You might say Sunday, 2 a.m. But if people are on holiday, then it's not 2 a.m. where they are. They might be on multiple time zones away using their card. And every transaction that goes through that's wrong costs somebody money. So that's pretty much the end for today. I did promise. Here's the link. You can go and get this code from Hazelcast's website, Hazelcast Jet's demo. In there's a few other examples of different things. So there's various things you can do with stream processing. What's nice about the image recognition is you can do it on a laptop. You know, it's not about big data in terms of width, it's about big data in terms of time. You want to get that processing done quickly. You have to process that image as it arrives. So last point, really, you need to be able to redeploy. You need all that kind of operational stuff around your grid that you can just scale it up and down. It's busy. A lot of people come through the airport today, add some more servers. Well, these servers cost you money, so if the airport gets quiet, you scale them down again. I don't really know why I'm obsessed about airports, but that's just a thing. You know, it's like the numbers might go up and down. For other businesses, maybe that's not true. But being able to scale down saves you money. If you're using less hardware and it's a pay-per-use model, then scaling down is good business practice. So just before questions, last point, my email address. If there's any questions afterwards, I'm going to be hanging about here for about 2 minutes, and then the next speaker comes on, so I'm not going to be here particularly long. But do we have any questions at this point? Shall I try the demo again, see if we can recognize a different picture? Anybody that looks like a chicken want to come forward and... Yep, question?
Why did you choose Java?
Whoa, that's a good question. So, question was, why did we choose Java for the implementation? Partly kind of historic. So, Hazelcast Data Grid started in 2008, and that was a Java caching product that's expanded to be many other things. Jet is just leveraging that same technology. So kind of inevitably, if you want to reuse it, you've got to be a JVM specific language, which doesn't give you a lot of choices. Because it's Java-based, it's pretty easy to find developers. One of the kind of things about other programming languages like Scala is actually resourcing projects resourcing projects with people is difficult. So partly historical, I think. In fact, it's about processing power, high-speed processing. Well, what does Java give for that? And Java 8 gives a lot of stuff that previous versions haven't. So lots of little JVM internal things are available. So this only runs on Java 8 and upwards. So if you're 6 and 7, then you should be upgrading anyway. But there's certain operations on the JVM internals that can be optimized. So one I'm familiar with is map entry set. And if you look at that, the difference between entry set on Java 7, and it's like it's giving you the whole collection rather than being able to drip feed you parts of it. And if your collection's large, then you run out of memory. Yeah, question?
I think in one of your early pictures you showed Jet and then the grid.
Yeah.
Are they on different sets of clusters, or are they on the same cluster?
Okay, so the question here was on this picture, that one. So do you put your processing engine in your grid, or do you have it separate? Whichever suits. The picture on the left is where each JVM contains a bit of the data grid, a slice of the data grid, and a processing engine. So you've got, in this case, 3 of them. So you have that locality of access. When that processing engine needs to access data in the data grid, good chance some of it will be actually in the same JVM. So that gives you a simplicity. But fundamentally, you're trying to solve 2 problems at once. You know, how many nodes do you need for your data grid is dependent on volume. How many nodes do you need for your processing is dependent on load. They might not scale together. You might need 3 of one and 5 of the other, which is where the separation comes out. But if you separate your processing from any lookup enrichment from a data grid, then there's a little bit of a network hop in there. So it's a no right, no wrong answer. You know, if you can, the picture on the left is the simplest. You just bundle them in the same JVM, deploy that one jar file, that one Docker image, whatever, super easy, and it has locality of access to some of the data. You know, but that kind of dissipates as the numbers go up. You know, if you're doing a lookup, and the data you're looking up is in one of the other JVMs, well, if you've got 3 JVMs and there's a 2/3 chance you've got to go out across the network anyway. If you go to 20 JVMs, then it's 19 chances out of 20. You go, unless you start doing things like key-based locality. But if you're just doing like a random lookup, then you know, that dissipates in worth at larger volumes. And you know, you might have other considerations as well. What happens if you need to take an outage on something for some reason? You have to do like a power off test or whatever. So you can have them separate, you can have them together. It's a kind of what's best for you kind of answer. Another question? Yeah.
Why was word count so much faster on chat? That was really something.
Oh, yeah.
High-level explanation.
Yeah, so the thing about word count, this case here, so Jet is super fast. I think I can give you like a high-level answer. I can't give you an exact detailed answer, but I do have a detailed answer available. I just don't have it at the top of my head. Basically, what you're looking at for word count is if you've got text and you stripe that across a map in memory, then you might have a line of text on one machine and a line of text on another machine. You can turn that line of text into individual words and tally those words on individual machines to get like a subtotal. And then you only do that last combination across the network where you're saying what's all the total for the word cat onto the one place. So you're trying to defer that kind of network transfer. So if your data is spread across multiple nodes, you can do most of that aggregation work in memory. And what makes word count fast in terms of Hazelcast is the processing uses bounded queues in between steps. So it's not directly this, the output, this goes to this. You're writing to essentially a ring buffer, which the other side is reading from, which allows for bursts of reads and writes. And if there's a little bit of clever scheduling that, you know, if your input queue is empty, then there's no point even being scheduled. Just keep giving the producer another go. So there's a little bit of internal magic in there, but it's not hidden magic. It's an open source product. You can go and look on github.com for Hazelcast Jet and see how it does it.
How much does it do to the acyclic graph versus the point pipeline?
Well, the acyclic graph is more of a methodology. And the only reason you want it acyclic is so you don't get stuck into deadlock loops. But
it's not the graph spanning that gives you the parallel speed up.
well, so what Jet does is if you define a graph, then it will send that to every JVM in your cluster, and then by default it will run as many instances of that graph as you have CPUs. So if you've got 5 machines with 4 CPUs, then you'll have 20 instances of that graph. And if you can parallelize your workload, you'll get higher throughput. So the idea is to try and make every CPU glow white hot, not have any idle resources. Last one, anyone? All right, I'm just going to do that one more time because I'm going to have one more go and try and recognize a cat. Why does it do that? My MacBook is frozen up. No, now it looks like my Mac is jammed up, so in that case, let's call it quits at that. So, yeah, go back to presentation mode. So there's the link to the demos, Hazelcast Jet demos. And that's my email address. Okay, thank you.